I'm going to model my Candium half-life, and what's different from the procedure, I've done it with 60 Candium's atoms. I didn't get that good a result or definitive result, so I'm going to try 100, which doing it virtually here is a lot less messy and a bit more practical. So let's put that aside and let's tip them out. And everything that has the M facing up, because I'm using M&Ms instead of Skittles, will be declared as decayed atoms. So 40 so far, 43, 46, 47, 48, 49, 50, 51, 52, there's another one there, 53. So I write that as decayed. So we have 100 and 53 have decayed, which means there's should be 47 left here that are undecayed. Alright, 47 atoms of Candium left. Let's have a decay incident. And I'm counting the decayed atoms. 21, 22, 23 this time. 23 decayed atoms. So I write that here, which means there should be, 24 atoms still stable. Here we go for our third decay event. And this time we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 decayed atoms. So I write that there, which should leave 14 undecayed atoms. And they go back in the cup. There we go. Our fourth decay incident. That one fell over there. And we had 1, 2, 3, 4, 5, 6 decayed atoms. So this is 6 decayed, leaving 8 left, and they go back in the cup. Okay, this is our 5th decay incident, and we have 1, 2, 3, 4, 5 that have decayed. So write that here, which leaves 3 left, and our sums add up because we really do have 3 undecayed atoms left. Okay, all 3 back in the cup, and we have 1 that has decayed. So for our 6th decay incident, we had only 1 that was decayed and 2 left, and now we have to keep on going. So we're going for our 7th decay incident, and we have 1 that is decayed. So we had 2 remaining, 1 decayed, and we have 1 left. So 1 goes back in. Right, our 8th decay. Now, this may not decay and it hasn't. So with our 8th go, we have no decayed atoms and we have 1 remaining. So it goes back. in our 9th incident, it still hasn't decayed, so we still have 0 and we have 1. And finally, we have a decay. So on our 10th trial, we had 1 decay and 0 remaining. So now we're going to graph this. Okay, I've ruled up my axes. On the x-axis, I've called it decay incident timeline because I might get these numbers to represent 1 year or 1 month or 1 day or 1 second. Half-lives of real radioisotopes have different timelines. A lot of them are in years, but some of them are only a matter of seconds before they fully decay. On the y-axis, remember this is my number of atoms. I had 100, so I have put graduations right on every 2 centimeters, and I haven't just written a number willy-nilly. I've made sure that it's like a ruler. It's got to be very accurate. Those of you going on to do a science, you'll be doing lots of graphs, and it's really important that you are accurate in drawing your graphs. And I haven't labelled this axis. It's going to be the number of atoms, and we're just going to leave it there, and it's Candium. Because if we do different trials, on the first one I did 60 starting atoms, and the second trial I did 100. If we've got time, we'll graph both of those to see if we get the same half-life. Okay, in the starting atoms, we started with 100, so I'm going to put a cross up here. In the first decay incident, the remaining atoms were, so this is remaining, not decayed. The decayed ones have gone. Okay, we're only concerned about what's left. We started with 100 after the first incident, so at time incident 1, we were left with 47 atoms. So we come up, that is 45, each square, 46, 47 will be exactly here. Second incident, we had 24 atoms left. So at time incident 2, we had 24. So 20 is 25, 24 is 1 graduation below. And we keep going. So I've plotted all my data, and I'm going to do a line of best fit now. Now, a line of best fit can be a curve. We can see that this is an exponential type shape graph. So that's the relationship. So even though we're doing a line of best fit, it's going to be a curve. And we don't sketch it, we just try and, we don't join up the points like a dot to dot picture. We are just going to draw the smoothest curve that goes through, and remember, and ends there. That's probably not very good, but it does the point. Now I'm going to graph the original trials with 60 atoms to see if we're getting a similar shape curve. Time to draw the curve. I think I might go this way this time. We're getting all the, trying to pass through as many points as possible. That's right. So for the first trial, 60 atoms originally. For half of them to decay down to 30, it is here on our graph. And the corresponding time is just over 1. Okay, now for the 100 atoms, their half-life will be when they reach 50 up here. So we go to the red graph and we draw a line down to the time there, which is just below, or a fair bit below 1. Now, why do we say half-life and we don't say full life? It's because of the shape of this graph. Look what happened with the 100 atoms. We had 3 incidents where nothing decayed. So if we were waiting for it to fully decay, we could get this result in this instance, and we could continue on for a while before we fully decayed. So it's more accurate to say, to pick a point of halfway for half of the mass of that element or substance to decay, and call it its half-life, because then we've got a more definitive result. This can go on for quite a long time, and if we wait till it fully decays, then we're open ourselves up to a lot of inaccuracy. So that's why we say half-life and not full life to decay.